This guide is for how to get the loads on anchors for lifting design for complex shapes, slabs with openings, irregular shapes, circular, etc. So we'll use robot for this, and what we can do is we can open robot, start a new shell design, and we open a blank page like this. We can look at the plan view, and we can start by adding nodes to represent the shape, and then basically join the dots to create our slab. So a few quick parts here. We open up our edit tab. So we start here by adding a node. So we'll start at our 0 coordinate point. At this stage it's good maybe to turn on your node numbers down here, just so you can see what you're working with. And we'll do that for now. Node 1. Here we've got a move or copy tool. So let's say we'll move that over 7 meters. So we'll make a copy of it over 7 meters in the horizontal direction. And we'll take those and we'll copy them up 2 meters in the vertical direction. It's essentially a rectangle. We're going to have a semicircular shape here, say. So if that's 7 meters, let's say this becomes 3.5, and then what we want to do is for the arc, move that up in the y direction 1 meter. So we'll click move here, move it up 1 meter. Okay, so for the arc we can go geometry, objects, arc. Now we have a number of different dialog boxes. Some of them might be closed, you can open them up here. And we've got 3 options on how to form it, depending on what kind of nodes that we're using. Here we've got the 2 end nodes and the middle node, so we can use this option here, beginning in middle. We want to split up the arc into a number of points, and we want to create the members so that we'll have every node along it available to us for joining the dots afterwards. So point 1 is the beginning node, so that's just 3. Point 2 is the end node, that's node 4, and the middle node. So that gets created there. And what I want to do is just get the node. So there's members automatically created, but we're going to get rid of those. So we can just select one, right click, select similar by cross section, and hit delete. So we're just left with the node. So I'm going to turn off the node numbers now for clarity, and then close that dialog box, and we close that dialog box. So we want to basically join the dots now to create our slab. So we can go geometry, objects, polyline contour. Again, another series of dialog boxes open. So we want contour selected, and we want down here we want the panel. So we want to create a panel around all these, and then it starts with first node, second node. You just click and join all the dots. You can see the coordinates being populated on the right hand side, so you can easily dip in and change them afterwards. Now when we click on the first node again, it'll automatically create. So we can close that. That's our slab created. We need to add the openings that we have in the slab. We need to add the thickness, and we need to add the lifting points. But add the thickness first. Over here on the right hand side we have thickness. We click on that, and I have a 400 slab put in here. Let's say this is a 250 slab. So we can put in new. So it's a 250 millimeter slab, 250 millimeters thick, and you got to make sure the correct material is selected. Some user-defined preferences are in here already for me, but you can select concrete, which will give you a the default concrete unit weight, which is about 24.53, I think, in robot. I've created a user one which is 25. It makes it easy for hand calculations afterwards for checking. So we can add that, close. That gets put up here, so we can select it and add it to that slab by just clicking on it. As a check, on the left hand side the properties come up. It's a 250 millimeter slab. Concrete user is selected. we can drop down that menu, and the unit weight, R0, is 25 kilonewtons per meter cubed. So there's two ways of doing the openings. We can do it manually, or we can use the automatic generator. So for manual, we need to add the nodes again to join the dots, and it'll take a cut out of our slab. So we'll take this bottom right node here, and we'll move it 500 mil to the left, and we'll move it 500 mil upwards. Make a copy of it, and the manual approach allows you to do more obscure opening shapes. So we'll do a triangle here. We'll make a copy of this 0.75, and if it's a triangle, let's say 375, and then we want to go vertically 0.6. I'm going to move that node, so that kind of creates a triangular set up there. So we go geometry, objects, polyline contour, and down here at the bottom we need to make sure the contour opening is selected, and then click in this box, and we're ready to go and join the dots. Then join, and it just takes that cutout for us. The automatic way then, if you go back into geometry, go to openings, an automatic generator comes in here. It's rectangle, circle. You can have a contour there as well, but it was more difficult to operate. So we go rectangle, we'll take one off the left hand side here. We can select the insertion point, so whatever our coordinates are based off of is going to be this point here in the bottom left corner, and the size of the opening we're saying is a 500 by 500. And what we want to do is tick these two boxes to lock them in place, which is the set out from the point that we're going to click on. And we'll say that it's 250 from the left edge and 250 from the bottom edge. So this now, we can hover over a few different areas, but from the 0 point, we're going to click here, and it comes in. So there are kind of two openings. Next step then is to add our lifting nodes. So take any point, and we'll move or copy that guy. So copy this guy, and it will go to, let's say, 0.75, 0.5. No, so we'll just copy him. Oh, he's too close. Move him over another 500 mil. There we go. No, move it up. Copy him up 1 meter, and we'll make another copy. Oh, too many nodes selected there. So just these two nodes all I want, and we'll say 5 meters. See where that lands. Oh, again, way too close. So we need to pull those back a meter, move them. Okay, so there's roughly 4 locations. And we go geometry, and we go supports. No, not releases. We want support, geometry, supports. So what we want to do is we want to put a support under each of these, but we want to make sure that the flexibility of the slab isn't restrained. So generally what we do is we would put a pin support under one of them. So pin support. We want a UZ support, which is just vertical. There. We want a UZ, which restrains the X direction and the vertical. So UZ. and that will go on the bottom left, and then a UI UZ, UI UZ, that will go up here. That restrains our slab. Okay, then what we got to do then is set up our load cases. So loads, load types. So we've got dead load, so that's going to be a dead load of the structure, so self weight. And then what we might want to do is we might want to amplify that dead load, so we'll do that in the combinations. So that's the dead load, and we can check by clicking on the load symbols, and if the outline is highlighted in red, it means that the self weight has been automatically calculated. So now we want to add some combinations. So from your calculations, you're going to have certain lifting coefficients added to the structure. So we want to multiply the self weight by, if we've got a lifting option 1, which is a tower crane, it's going to be a 1.2 factor. If we've got option 2, it's going to be 1.4 factor, etc. So we'll just say lifting coefficient, and we hit OK. So we click on our dead load and factor 1.2, and then hit apply. Okay, we can create a new one for our ULS conditions, which is going to be the lifting coefficient. The self weight times the lifting coefficient times the 1.2 for ULS on the dead load, or 1.35, whatever you select. So we can use 1.2 there as well. Okay, apply. So, and so we can populate that. We can then run our model. Calculation button up here. The mesh is quite coarse, so if we want to change our mesh, we can bring up this dialog box, which is this mesh guy up here. Options, typically a 1:1 or 1:1.5 ratio for the element size. So if your slab is 250 thick, we could say the mesh size is 0.25, and we can run that again. Looks better. Okay, so we end up with something like this. So we can clean up our model. So this bottom right guy here, default display, just cleans up the model a bit, and just for clarity we can turn off the the mesh. We can also turn off the panel interior, just so we can see the reactions a bit clearer. And we want to get results diagrams for members, reactions, and we want DFZ reactions. We'll click on descriptions, we'll apply. So these are the reactions. I've actually spotted that this support is actually incorrect. Geometry, supports, that was our UI UZ, and we had actually incorrectly said it was UX UI. So turn off the UX, turn on the UZ, hit add. That'll change your calculations, so that's changed. So that means you have to rerun your model again. And we end up with a number of different values here. So the idea of this is that because it's an irregular shape with openings, the distribution of the loads between all nodes is going to be different. So you can see these upper two nodes are taking a lot more load than this lower node, and also this assumes that all 4 lifters are engaged. What we can do is, if we go top view, we can make a copy of this if we're saying that there's only 2 lifters engaged. So we can check that as well. So 2 lifters engaged are going to be on the diagonals. Minus 5 on naught. And we make 2 copies to check the worst case diagonal. So we can go to our geometry, supports, we can delete, let's not clean up our model. We'll just for clarity, we'll delete the mesh just so we can see our nodes. And we want to delete that node, and that node, that node, and that node. Okay, so we run the model, we'll get an instability error, but we should still be able to get the correct vertical reactions. So we'll clean our model there again, turn off that, turn off the mesh, and we want to get the results. We'll just turn off that box. Results, diagrams for members, reactions, FZ, apply. No, descriptions, apply. Okay, so we can see here that the bottom combination of 2 nodes on the diagonal is going to be give us the worst case, 71.16. So essentially that was the self weight only. We can go up here to look at the load with our lifting coefficient. So our lifting coefficient was 1.2. So obviously 71.16 times 1.2 is 85.39, which is what we have here. And then for the ULS condition, there was another 1.2 on top of that, which was 102.47, which is what we have on top of this. Another sanity check is to make sure that these loads are correct. So if we go back to the self-weight combination, we've got a number of values here. So all 4 of those, if we add them up, 43.56 plus 55.62 plus 6 plus 8.67 gives us 113.85. 113.85. We know it's 250 thick. We know that this shape has an area of 18.22 millimeters squared. So 18.22 is the area times the thickness of 0.25 times the unit weight of the concrete of 25 gives you 113.875. So a small bit of rounding there, but yeah, once you're within 1 kilonewton, you'd be happy that the results are correct.